So we are continuing our discussion of hybridization, the reason why, when we use it, how we use it, and what we get from this theory. So as a little bit of review, I want you to understand that this theory, of course, is for the central atom in covalently bonded compounds, and that we are mixing or hybridizing orbitals, and they allow us to give us the three-dimensionality, the bond energies, the polarity, and of course the bond angles. So I started with the discussion of the BF2, and BF2, of course, all right, has this configuration. If we excite it, we open up two possibilities, and quickly, all right, we do the Lewis dot diagram. I get something like this. B has two valence electrons, and fluorine has 7, as we see from its configuration. If we were to put it together based upon an s orbital and a p orbital, based upon the excitation that would occur, energy coming into this to excite this electron to a p orbital, like so. So we're going to basically bond and fill these orbitals, and that's what bonding is, essentially sharing electrons in orbitals, okay, that are more stable this way than they would otherwise. But the problem is that when we take an S and a P, what we're going to do is we're going to wind up with a bond angle that's about 90 degrees here. And we know from experiment that that doesn't exist. Also, when we break the bonds between the beryllium and the fluorine, we notice that the bonds are exactly the same bond energy. Yet the bond to break this one would actually be higher because an S is more stable than a P. Okay? So again, now I'm drawing the S's because just drawing them smaller in the same angle just so that we can see the P's. All right. So then when we do the sketch of the hybridized molecule, having an S hybridized with a P, what we get, one S and one P gives us two orbitals in, 2 orbitals out, we get 2 sp orbitals. And they would surround this central atom, remember this is beryllium, and they would repel themselves to get that 180-degree bond angle that we see experimentally. And it would also give us the bond energies, the energy to break these stable scenarios. And these bond energies, of course, are somewhere in between the high energy to break an S and a low energy to break a P. It's something in between. So it's supported. This theory is supported. Now, important, fluorine, which has one p orbital non-filled, and that's the one we're overlapping, okay, just had one of them, okay, is a terminal element. It doesn't need hybridization because it can successfully bond by one direction. By having 2 electrons in this orbital, now this orbital is filled, and it could never bond to the opposite side. And that's why hybridization is important. You can't, if you're going to be a central atom bonding to opposite sides, especially 180, you can't explain that with a p orbital. You can bond to one side or the other, as F is doing. And it's a terminal element because it only makes one bond from one side. Okay, very important. So let's go on and continue on our discussion with the back side. Now, here we're dealing with carbon. And carbon can have different types of hybridization, but we're going to focus mainly on the hybridization of carbon in sp land. Okay, now of course it's an sp ditto, so I'm not really giving away the farm by telling which one it is. But here's carbon's electron configurations: 1s2, 2s2, 2p3. And of course, you can think, well, okay, it could possibly bond it to 2 different things, but again, energy coming in, and we excite, okay, these electrons. This electron can jump out to the empty one, and it becomes this scenario. And what happens, so we think in the theory, is that an S, in this case a 2s2, or this would be 2s1, I guess. This 2s1 and this 2p1 would mix to make 2 free orbitals. And you may say, Mr. Grodsky, unlike the first page, what about these 2? Why aren't these going to be hybridized? Well, the Lewis dot diagram will decide for me whether we're going to mix 2, 3, or 4. And that's important. Again, it's an SP ditto, a worksheet. So it kind of tells that. But let's go to the Lewis dot diagram because it's really going to tell us a story. So let's do CO2. And how do we do that? We're going to put carbon in the middle. All right. And normally the more electronegative atom is on the outside, but in this case I have two things, so I can guess that the carbon is in the middle. All right. And I'm going to start putting my valence electrons out. And that carbon has 4 valence electrons. 1s2, 2s2, 2p2. So it's got 4 valence electrons, not any filled energy level. And then we know that oxygen has 6 valence electrons. So I'll put a pair here, start with a bond. It has 6, so 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And then, of course, you can see here, I know that my oxygen wants to have 8 to fill its energy level, right? The 1s2, 2s2, 2p4 wants to become a 6, so it wants to somehow share 2 more so that it can have a total of 8 electrons that would fill. Right now it has 6, but we can push it to 8 if it shares 2 more. Okay, so right now by sharing I can count 1, 2, 3, 4, 5, 6. Okay, now I don't think I have the right number of dots here. There should be 6 red dots here just to do this. 1, 2, 3, 4, 5, 6. So carbon has 6 valence electrons. Okay, and it's going to take 1, 2, 3, 4, 5. One of it is going to be in the bond. Okay, so I started that incorrectly. So the first thing you do is you put out all the valence electrons. And I essentially put 1 with each atom to a bond. So carbon has 4. I put 1 with the oxygens to make 1 bond and let the rest sit there. And now I'm going to evaluate for those that haven't done this. 1, 2, 3, 4, 5, 6, 7. This has 7, so this is not going to work. So what we're going to do is we're going to take one of these and we're going to move it and make another bond. Same thing over here. And that's really all you can do in a scenario where you need more is you try another bond. And in this case, I'm just putting one from the other. And now that I count, okay, I can see that I have 8 for the oxygen. This is not 8. Okay, this is 7. So the same scenario exists on both sides. So I'm going to take one of these reds, move it over, take one of these blues, and I'm going to move it over. And now you can see what we have here. Very important, the Lewis dot diagram. We're putting the right number of electrons in a bond so that each of the atoms involved are sharing, in this case we call it an octet, 8. And 8 fills the second energy level. And of course carbon also is sharing 8. So that is the Lewis dot diagram. Now I can write this another way. I can write carbon, and I can write 2 dashes. Each dash is a pair of electrons. But I must show the lone bonds, the lone electrons that are left over. So 2 dashes on both sides. Now you may say, Mr. Gradsky, well, how do you know this shape this way? Well, here's what I do know. I know this because of something called VSEPR theory, that these pairs of electrons that are being in the bond would repel themselves into a linear 180-degree shape. So because these electrons, okay, are located locally between the atoms, and there is no lone pairs, right? There's nothing left in the carbon. And the oxygen has some lone pairs. I forgot to write the second lone pair there, okay? So the carbon has no lone pairs. Let's pretend it does. That would push and repel these electrodes into a different shape. But because we figured it out from doing the Lewis dot diagram that there was no lone pairs, that this is going to stay linear. So my Lewis dot diagram, just following the rules of valence electrons and putting them each one together and keep doing so that each one has its stable configuration of a noble gas, gives me a shape that I can predict, and I predict that it's linear. And we are right. And because it's linear, oops, there's a doohickey. Because it's linear, oh my gosh, double doohickey, okay? Because it's linear, the hybridization must be SP. So that tells me from the Lewis dot diagram that I'm going to take an S and a P and hybridize it. And as we've done before, an S and a P gives me 2. So the carbon is going to be in the middle. What we're going to have is we're going to have an sp orbital here, and we're going to have 2 of them. Why? one S and one P make what? Two orbitals go in, two orbitals come out. Now, I'm not in love with that sp orbital, so I'll try again. All right. And they should be exactly the same size, although I'm doing the best I can. And what happens is these electrons in these orbitals repel themselves to 180. So two new orbitals, this S and P, mix together to give these two. Okay, how many valence electrons do we have? We have 4. I'm going to put one here and one here. Now you may start saying, Mr. Grodsky, wait a minute, what happened to the two other P's? Well, they did not get hybridized, okay? So they're in here, and we're going to draw them now, okay? So remember, the S and P hybridized, but these P's did not. So I'm going to draw a PY. I'm going to draw it skinnier because it's a dumbbell shape. So this would be PY. And I'm going to have one coming out and one coming in. This would be my PZ, if you can see that. And I put the electrons in both. So here's electron. We have 1, 2, 3, 4. 1, 2, 3, 4. Okay. So if you can think about this being left and right, up and down, this coming out to you and this going into the board. Now let's draw the oxygen. As I said before, the oxygen is bonding at the end. So the oxygen doesn't need hybridization. Okay? So the oxygen is unhybridized. So it's going to have an unhybridized P. This would be its P, let's say X, PY. Then we have the P coming at you, behind. Don't lose sight that this right here is one orbital. This is PZ in the house, yo. PZ. This would be PY, right? This is PX. These are the same orbital one, okay? So let's put, and of course we have an S. Now again, just drawing the S smaller so we can see it. Let's put the valence electrons in. Let's make them red for oxygen, as I did in the drawing. So it has 1. This guy's filled. 2, 3. Let's do 4. What? 5. And 6. I counted 6 valence electrons. Now, if you're not following me, what's oxygen? It's 1s2, 2s2, 2p4. It's got 6 valence electrons. It's got 4 in its p. Count with me. 1, 2, 3, 4, and 2 in its s. 1, 2. Okay. Now let's draw the other side. Okay, the other side looks exactly the same. We're not quite done yet, but just follow me. This is another. Let's make it blue. Okay, so we've got a p orbital here. One going up. One going down. One coming at you. Good. Let's draw the S so that the P's stick out. And we put 6 valence electrons in. 2 in the S. Then we have 4 in the P. 1, 2, 3. Okay. Let's go 4, 5, and 6. I put them a certain way. Now, if you notice, party people, what we have is we have one bond. So one of these bonds right here, I've circled. So you only have one of the bonds. And we call this a sigma bond. It's my sigma. A sigma bond is where we have direct overlap of 2 orbitals. It's the strongest bond. Okay? If you notice something, we're missing the second bond. Well, we can't put another p orbital because it's just sterically, it's impossible to bend another orbital here. So what we're going to do is watch. I'm going to make this show you. The next bond, and we should understand this, bonds occur because of sharing of orbitals. Notice this orbital, the 2py, is in the same plane as this 2py. Notice this has 1 electron, this has 1 electron. What can happen, party people, is this electron can basically move back and forth above and below the plane of the nucleus. It's a weaker bond, but this is one orbital. This is one orbital. They're sharing 2 electrons, just like the sp here is sharing with the unhybridized p. So these 2 unhybridized p's in the same plane of oxygen are sharing this bond. We call this a pi bond. And this is not 2 bonds. This is one. This is the same. The above and below represents the same bond because it's what? 2 electrons being shared. If you think with me, if I do the orbital notation of oxygen, we know oxygen S is filled, and it was what? 2p4. So this electron here filled this orbital, and this electron here fills this orbital. So this, you can think of this orbital here is what's involved in the pi bond. It's weaker, okay? But that's the what? That's the second bond. And then, party people, we have the other bond. Look here. There's one, and there's one here. If you can see it, there's one in front and one behind. So we got a chain link fence. We got in front and behind, and that's another pi bond. And that represents the second bond on this side. Now, I know it's tough to see it, but three-dimensionally, we have something sticking out. And there's a bond in front and behind, the same way we have top and bottom. And notice I drew what? One here and one here. There's one electron in this p orbital and one here, and now they're sharing. These are weaker bonds, okay? But a pi bond is kind of like, think of it, a perpendicular bond between unhybridized orbitals. Never going to be as strong as a direct overlap. Don't forget, direct overlap, it's direct overlap between what? The nucleus. Here, the nucleus in a pi bond is not exactly in between. What makes a chemical bond, party people, is the simultaneous attraction of electrons between the protons. So party people, it's a stronger bond when you have what? Directly. So sigma bonds, which are direct overlap, are stronger than the pi bonds. But the pi bonds certainly give stability to it. And the reason why CO2 is stable, it's released in cellular respiration and eventually gets to the plant, is because it doesn't break down. It's low energy. And the reason why it's so low in energy, it's got 4 bonds between the carbons and the oxygens, 2 apiece. Those pi bonds add to it. All right? A lot to take in there. But before we finish, let's talk about hybridization, sp. Okay? Bond angles, 180 because it is sp. Now, let's talk about bonds. These electrons that are between the bonds in the carbon, okay, we're going to call these polar bonds. And you say, Mr. Gratsky, how do I know that? Well, polar bonds exist when electrons are shared unequally. Carbon and oxygen have different attractive forces for their electrons, right? Oxygen is closer, has a higher Z number in the same what? Energy level. An easier way to say that now, it has a higher electronegativity, so it pulls this pair closer. So if I was to draw this better, oxygen kind of pulls the 2 pairs closer from the carbon. And when that happens, we say that you have most of the electron density between the bond on the oxygen ends. There's a difference. Polarity means differences. So it's a polar bond. It has polar bonds, yes, because it shares unequally because of 2 different nonmetals. Is it a polar molecule? The answer is no. If you look at the entire shape of the molecule, yes, they're sharing electrons unequally, but they're sharing unequally equally. What I mean by that is you have the same what? Polar bond on this side creating what? A lot of electron density right here. Because you have the same polar bond pulling on the electrons this way, you have the same electron density over here. So this side of the molecule has the same number of electrons as this side of the molecule. So there is no difference in charge, so it's a nonpolar molecule. In Regents chemistry, we would say because they're symmetrical, the polar bonds would cancel out. Okay, so this is nonpolar. All right, let's go down to the next one. Good times. All right, we always start with the Lewis dot diagram. I'm going to move a little faster. Got carbon, 2 carbons now. Those are my central atoms. All right, just going to throw my H's here. I may not know where they go, so sometimes this is trial and error, but I do know carbon has 4 valence electrons, so I draw them. And I'll make a bond here. All right, now hydrogen, we know has 1 valence electron, so it brings that to the table. And now, if you can't see this, evaluate. Okay, hydrogen feels like it has 2. That's a good thing. It's as stable as helium by sharing. But carbon does not feel like it has 8. That would fill the second energy level. 1, 2, 3, 4, 5, 6. So both have 6. Okay, so what do we do? Well, like we did before, we're going to add another bond. So we're going to bring this one closer. And then we'll bring this one closer. And then we evaluate again. So hydrogen has its 2. And then you look for carbon, it's sharing a total of 2, 4, 6, 7. Not going to work. So if you haven't guessed already, here's a scenario where we're going to have a triple bond. All right, so we're going to basically move this over. And then move the other one over. That's really all you can do. So this is kind of a game and a puzzle. And you keep doing this until you get a stability of electrons for each. Hydrogen wants to have 2, be 1s2. And then if you look here, party people, you can see that the carbon, this is sharing 2. This carbon by sharing feels like it has 8. So both carbons by sharing feel like they have 8. Okay? I'm not going to do this anymore. You should be able to figure this out from this point forward. Now, what do we have? I can redraw this. Carbon is triple bonded. Each pair is a dash. And you notice something. I'm drawing it linear. Why? Because there isn't any lone pairs of electrons above or below to bend this downward. Okay? So you have to have lone pairs or something just hanging out here. Notice in the drawing above, Mr. Grotsky, you have lone pairs here. No, I don't. They're involved in a what? The second bond was the pi bond. Front and back, top and bottom. Okay, if you think of a chain link here, the chain link in front. But the bottom line is these were not just hanging out, they were part of the bond, so that doesn't count. So because there's no lone pairs of electrons to bend these electrons downward into another shape, I know it's linear. And because the Lewis dot diagram reveals that to me only when I do what? Do this, I know that the bond angle is 180, and I already know the hybridization, of course, is SP. I knew that because, well, we're dealing with a SP worksheet, yes, but I'm showing you how this comes to be. So because it's 180, an S and P come together. So here we go. Here is one SP. There's going to be 2 of them because an S and a P are separate orbitals. They mix. 2 come in, 2 come out. We put the electrons in. Okay. Remember, we're drawing 2 carbons here. So this would be the first carbon. The 2 inner carbons are going to be the ones. So we can draw another carbon. So this is 1 carbon. And here's my other carbon. These are both SPs. And we notice we're going to make 1 bond here. And that could be, right now, this bond. Ooh, means you have 2 more bonds. Well, if it's SP hybridized, as we've learned, and S and P came together, we have 2 unhybridized what? P's. That's right, for each carbon. So we're going to draw that. So I'm going to go above. Here's my 1 unhybridized P. It should be thinner in a dumbbell shape. This is 1 orbital, PY. This is another orbital, PY. I got 1 coming at you. Going into the board. 1 coming at you. And going behind you. Let's put the electrons in. Well, think ahead. I want 1 pi bond on top and bottom. That's why I'm doing that. So that will have 1, and then this will have 1 here. So each one has its 4. 2 in the P, and 2 in the, well, here's the 4 valence section. 1, 2, 3, 4 for this one. Let's change the color for the other one. 1, 2, 3, 4. Okay, and then of course hydrogen is going to be what? It's 1s1, and it's unhybridized because it's at the end. It brings 1 electron. There it is, and there's your sketch. Look at it, it's linear because it's sp, but we forgot a couple of things. What did we forget? The pi bond above and below, and front and back. These are my pi bonds, and this right here is my sigma. Polar bonds, and these are nonpolar bonds. Well, there's nonpolar between the carbon and carbon, but there's definitely polar bonds between the C and the H. They're 2 different elements. They're sharing unequally. Carbon's a little more electronegative, so it pulls it in. So yes. Is it a polar molecule? No. Okay, is there more electron density on one side than another? Because of its symmetry and the polar bonds are the same all the way around, it's a non-polar molecule. Moving on. Now, some people are having some difficulty with the bonds and the molecule. If I was to draw a molecule like this, remember molecules have an exact finite number of atoms in a shape that we're trying to figure out through Lewis dot diagrams and explained the best, needing hybridization to explain what we know. If there are more electrons on one side of a molecule than the other, we would call this side the negative side and this the positive side, and that's our polar molecule. What creates an unequal distribution of electrons is an unequal sharing of electrons. So to be a polar molecule, you have to have an unequal distribution of electrons. In the case above here, in C2H2, acetylene gas, okay, which we actually used in our pumpkin demonstration, all right, well, this is a nonpolar molecule because the electrons are essentially what? Shared evenly throughout the molecule. So because it's linear, there should be 1 bond here. Because it's linear, there's the same amount of electrons on both sides. So if I draw my circle, I've got some electron density in the middle, and then I have some place here. So if you can see, electron density is pretty even throughout. Now, even though there's we have to understand something, hydrocarbons, carbon-hydrogen bonds, even though these are 2 different nonmetals, okay, I made a little mistake here. This is actually going to be a non-polar bond. So polar bonds, we would say X here. Carbon to hydrogen have about the same electronegativity. Carbon's about 2.6. Hydrogen is about 2.2. So that difference is so slight that they're sharing electrons just about evenly. So we consider this to be an equal distribution of electrons, and therefore there's really no differences on one side or the other. So this clearly has no polar bonds, so no. Polar molecule, no, because you have to have at least some polar bonds to create this movement of electrons. So hybridization, of course, we needed it for the 2 carbons here. Okay, moving forward. Okay, if I'm being redundant for some, I feel bad, but now I'm over it, making sure we're learning a bunch of things here. Okay, now let's go on to CHF. Okay, we've got 2 carbons. We're going to have to put an H, and this time we have an F. Carbon has 4 valence electrons, and we can do this pretty quickly now, right? 1, 2. Now we just did this one with one terminal at the end. You can probably guess it's going to be another triple bonded compound. And then fluorine, hydrogen having 1 and fluorine having, remember, fluorine has 7 valence electrons. So that would be at 7. And if I'm going to draw this with some sort of accuracy, let's draw these electrons held a little bit tighter to the fluorine. Okay? Because fluorine's more attractive to electrons than carbon. Okay, these are shared down the middle, poorly drawn, but hey, I'm tall. Okay, and these are about shared. So we would consider this to be essentially a non-polar bond. Obviously the same atom, these are non-polar bonds, but clearly there's some polar bonds here. Why? Well, there's a difference in attractions. F is the most electronegative. It loves to attract the negatives, electronegative, so it pulls that pair closer. All right, that's what makes it a polar bond. All right. Now, let's think of the structure. Because in my Lewis dot diagram, for the same reasons above, there's no lone pairs above the C, there's no electrons to push it down into any other shape but what? Linear. Okay, so therefore the bond angles are 180. Hybridization, we're going to guess, is SP because our Lewis dot diagram is suggesting that this has to be linear. There's no lone pairs, unbonded electrons in between. We'll eventually get to those. Okay, so we have polar bonds. Yes, we do. You have some nonpolar ones too, but we definitely have some polar bonds. Okay. Now, before we can suggest that the entire molecule is polar, we have to be very careful we know the shape. So the lone pair up top is suggesting it's linear, and it is. And because it's linear, okay, if I was to draw a representational molecule like that, okay, the electron density in the middle is about the same. These are about the same. Carbon and hydrogens are nonpolar, but fluorine pulls that pair between the carbon more this way. So fluorine has more electron density at the end. So this will make this molecule a little bit negative on this side. And because this side doesn't have the same density on this side, a little bit positive. And that polarity means the molecule's polar. So in order to have a polar molecule, you must have at least a polar bond normally. Okay, there's one example that I'll get to. But it's a polar molecule. Now that I know the shape, it's not the same all the way around. Okay, and in any case, let's draw the shape. The two carbons, because there's no lone pairs, have to be linear, are sp hybridized. So let's get to it. There's one sp hybridized orbital, and there's another. Fluorine is a terminal atom. That means I do not need to have hybridization to explain its bonding. It has 7 valence electrons. It has a unhybridized p that has 1 already, right? And then it's going to have an unhybridized p. The whole thing is unhybridized, so I have to draw the 3 p's. This is coming at you and into the board. And then we have our s's. Okay, put the rest electrons in. We have 1 here, 1 here. Okay, and then 1, 2, 3. All right, be careful. We have our triple bond here. Let's do the unhybridized p's for the carbon because it's S and P. There's how many unhybridized? There's 2. Right? If S and P comes together, that means there's going to be, this is only one. This is P, Y, and then we're going to have one that comes out at you and then into the board. This is PZ. Okay. Now carbon has 4 valence. I'll draw them in black. So here comes 1, 2. All right. And then of course it has, let's do 3. And then we'll do 4. Now fluorine's terminal. So I'm not sure why I paused there. I guess I was just having a brain hiccup. All right. So we have 6. Remember, fluorine is 1s2, 2s2, 2p5. So it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Notice I don't put 1 here because 2 will fill it, and that's a sigma bond. So I just did this bond right here. Okay. Now we have another carbon who is sp hybridized. So here's one other sp overlapping. And there's another sp overlapping. And because it's sp, and there are, for what? Carbon is what? 2s2, 2p2, and 2 of those s's jump to the what? to the P's, what we have is an S with 1, and each what? Each P has 1. Remember, we hybridized these two, so we have 2 unhybridized, okay? Again, just keep it all straight in your head. 2 are hybridizing, but then there's 2 others that are unhybridized, and I draw them. Here's my 2py. Here comes the X at you, and the X in here. I don't draw an S for these 2 because the S has been hybridized. And let's draw the black. So here's another 1, 2. Let's go 3 and 4. Now I'm doing it in a way so pi bonding can occur. Let's finish the H. The H is 1s1, so it's just a sphere. Overlaps directly. And there is my other sigma bond. Sigma bond here. 3 sigma bonds overlapping. Now I'm going to put my pi bonds. Okay, let's do that. I don't know, in orange. So here's the no pi bond here because these are all filled. Okay, bad Grotsky. So here's my, remember the triple bonds. You have your first bond, which is your sigma bond, and a second and third are going to be your pi bond. So here's the first. My first pi bond, which would be the second bond here. And the second is going to be what? Front and back. And notice these 2 orbitals are feeling like they have 2. They're sharing electrons. So 2 out of the 3 are the pi, and every time we have a single bond, every time we have a single bond, let's make that red. That is a what? A single bond. So the sigma is always the single bond. If you have a double or triple, you have more. So the moral of this story is anytime you get a single bond, it's a direct overlap. A second and third bond in a triple bonding scenario has to be these pi bonds, these perpendicular bonds, because if you're overlapping directly in one dimension, you can't physically push these together to overlap. So they have to do this kind of weakening perpendicular type bonding. That's why the second and third bonds are never as strong as the first overlapping. Okay, so moving forward, down last to nitrogen. Okay. And I'm going to do this really slow because people are playing this way too fast. Just kidding, I can continue on. All right, so here's nitrogen, and it has 5 valence electrons. 1, 2, 3, 4, 5. This one has what? 1, 2, 3, 4, 5, and you could probably guess what's happening here. All right, just making sure you get this. This nitrogen feels like it has 2, 4, 6. Same thing for the other nitrogen. So what do we have to do? We got to put some bonds together. Okay, so I'm going to put a black, okay, over here, and the red that was over here, I put here. And if you reevaluate, what do you get? 2, 4, 6, 7. Who do we appreciate? Grotsky for these videos. So what we're going to do is we're going to take this black one. Booyah. Yeah, bring it back. Put this here. And then move this red one. Oops. Not add a red one. Remove this red one. Yeah, boy. And we're going to put that one here. Don't know why they're sliding down. But what we have is a triple bond. My gosh. Now you may say, Mr. Grotsky, I got some lone pairs. But these are both terminal, aren't they? Let me rewrite this nicer. Here's an N, and we have sharing these, and then we have these right here. Now, some people would suggest that nitrogen is hybridized, and they would say, think about it, it's the same reasoning. You're going to have a lone pair sticking out. And some people would suggest that this is hybridized. And I could make a case for it, okay? But to keep in line of what we're talking about, I'm going to suggest that you really don't need to explain it as hybridized. Now, people do know that you can bond to the ends. The question is, do they stay hybridized? Now, for those that don't see what I'm saying, isn't this shape of having one bond at the end or a filled orbital very much like what we just did here? Absolutely, look at this. So people say just because you don't have an H there or something at the end that you don't need to hybridize, or it looks like it's hybridized. So I will go either way with this, and people have fought me online, but I want to say, do you need hybridization to explain this? And I suggest you do not. Why? Well, here's my nitrogen, okay? It's bonding terminally on one end. It's not really a central atom, so I'm going to say no hybridization needed. So how do I explain it? Let's see. Here's one N. Here's an unhybridized P. Nothing is hybridized here in my drawing. I have an S. And I'm going to draw another N. Let's draw another color to keep things simplified. So I got one overlapping, what kind of bond? You bet, sigma. One coming at you, and a circle. Okay, so put the electrons in. Here's one for that end, and a black one for this end. There's my first bond, which could be my first sigma bond. Then I put the valence electrons in. There's 5, so this is the black one. 1, 2, Christmas. There's a doohickey. They show up sometimes. 1, 2. Let's do 3, 4, and 5. I put the 2 in the S, and then 2 more, and 1 each in the P's. If you think about that, 1s2, 2s2, 2p3. 5 valence electrons. What's that going to look like? Here's an S, and here are my P's. This is filled, and we have 1 apiece. That's not hybridized. So I have what? 3 electrons in 1, 2, 3 orbitals. The one that has 1 overlaps the other one that has 1. So it's going to have 1, 2, 3, 4, and the same idea. I'm going to put 1 in each. So 1, 2, 3, 4, 5. And you can see where the pi bonding is going to occur. Okay. And let's make that a nice color. Let's make it yellow. Here's the 1 pi bond. This is the same pi bond because it's the same orbital overlapping. Another front, another what? In back. So we've got 2 pi bonds, and this one in the middle is a sigma. And there you go. I think I can explain this bonding without hybridizing. Now, people would suggest, tell me, based on the Lewis dot diagram, don't we have a pair of a lone pair here? And my suggestion, and some people would disagree with me, is that as soon as you make the bond here, then it becomes a central atom and hybridization is needed. Hybridization is just a theory to explain what we have. I can explain this because they're essentially bonding on one side. They're both terminal atoms. It's only when I have a central atom do I need it. This is not there's no central atom here, unlike all the drawings. So no hybridization. This is not a there's no polar bonds here. They're sharing electrons equally because they have the same attractive or electronegativity. They're the same element. And they can't be a polar molecule because the electron density is exactly the same for all of them, right down the middle. Okay, so it can't be a polar molecule. All right, and of course, this has a bond angle. You could say it's 180, okay, because it's straight across, but it's just, you really can't say it's a bond angle. I mean, if two things bond, it's just there. Until you have a central atom, do we consider a bond angle? All right, now I do want to revisit this C2H, C2HF. I lost my voice here a little bit. Okay, this, of course, is a polar molecule, and I want to explain it a little better. Okay, so polar molecule, yes. And what we do is draw something called dipole moments. Okay, who is the more electronegative, the carbon or the hydrogen? We would say the carbon in this case. So we'd write negative, and I put a positive here. Carbon's better at pulling electrons. And we draw something called a dipole moment. We point how this pair would be pulled. This pair is pulled a little closer to the carbon. Now, in truth, these bonds are essentially nonpolar, but there's a little bit of difference. So this arrow should be small. There's no dipole moment here because they're the same exact pulling. But carbon And fluorine is a huge, huge negative on this side. And this is a little positive. How do we draw it? From positive to what? Negative, we draw these arrows, and this is a bigger arrow. So these dipole moments flow of charge. I've got two arrows going this way, so for polar molecules, we tend to write an overall dipole moment, a flow of charge going to the right. Okay? The ones that are what? Non-polar, like this one, okay? Even though carbon's a little negative, and these guys are little tiny positives because carbon's a little more electronegative, the flow would go what? To the carbon a little bit. Because these two arrows are going to be the same size, they're called vectors, because the difference in electronegativity is about the same, they cancel out. And when dipole moments cancel out, you have a nonpolar molecule. Here they don't. Okay, just giving you that. All right, so a lot of information here. We're going to keep going and keep working on the same things. So we learn things about sigma bond, which is the first bond, which is an overlapping, and anything past a sigma bond has to be this perpendicular bonding that must occur with unhybridized P's. Must occur. Okay? All right, enough of that.